What if the galaxy you live in is nearly twice as large as every textbook told you, and the mistake that hid its true size persisted for almost 100 years? Tonight, we trace a measurement that seemed certain, that appeared in classrooms and planetariums and popular science books for generations, that shaped how billions of people pictured their cosmic home, until better instruments forced scientists to admit they'd been drawing the boundaries too close, the edges too neat. The Milky Way, this river of stars you drift through while lying in bed at night, this spiral structure holding your sun in its slow 200 million year orbit, is not the size you learned in school. And the reasons why take us through cold mountaintop observatories, through photographic plates exposed for hours in darkness, through hidden clouds of dust that fooled entire generations of astronomers, and finally, through satellites measuring billions of stars with precision that seemed impossible just decades ago. Welcome back, traveler. Tonight we drift through science. You're lying in your bed right now, or perhaps you've settled into the corner of a couch, the room around you dim except for the pale glow of your phone or the soft light bleeding in from another room. The pillow cradles your head with familiar weight, the blanket holds warmth against your skin, and somewhere nearby the quiet hum of a refrigerator or the distant sound of traffic reminds you that the world continues even as you try to step away from it. If this kind of astronomy brings you peace, if falling asleep to stories about cosmic mistakes and slow corrections feels like the right way to end your day, you can tap the like button or subscribe to let me know there are others out there who need this too, who want to rest while learning how humans measured the galaxy wrong, and then, with patience and better tools, measured it right. It's completely okay that you're awake right now, that your mind won't settle, that tomorrow feels too close and today won't quite let go. Maybe you've tried other things already, scrolled through feeds that made you more anxious, closed your eyes only to find thoughts racing faster in the darkness. That restlessness is normal, and you don't need to fight it here. You also don't need to understand every word I say tonight. Don't need to remember the numbers or the names of scientists or which telescope discovered what. If your attention drifts, if you miss entire sections because your mind wanders to something else, if you fall asleep before this story ends, that's exactly what this is for. You're not being tested. There's no quiz at the end. You can simply listen, let the words wash over you like a tide, and allow the images to form and dissolve in your mind without holding on to them. Tonight, we'll walk slowly through the story of a galaxy measured too small. We'll talk about spiral arms and stellar distances, about Cepheid variables that pulse like cosmic lighthouses and help astronomers calculate how far away things are. We'll discuss the disk of stars rotating around a bright central bulge and the ancient halo of globular clusters orbiting far above and below that disk. But we'll also spend time with the people who did the measuring, the astronomers who spent freezing nights at telescope eyepieces, who developed glass photographic plates in chemical baths by dim red light, who built satellites and launched them to points in space where they could measure 1 billion stars without Earth's atmosphere blurring the view. This is something I always try to show you, this human side of discovery, because the universe isn't just something that exists out there. It's something people explore, with instruments that break and data that contradicts expectations and mistakes that take generations to correct. That's the real story, the one worth falling asleep to. So let the room around you fade a little. Let your shoulders drop, your jaw unclench, your breathing find its own slower rhythm. We're going to begin with a question that sounds simple. How wide is the Milky Way? And follow it through a century of observations, through errors and corrections, through dust clouds that hid the truth and new instruments that revealed it. You don't have to stay awake for all of it. You don't have to remember anything when morning comes. You can just be here in this moment, while something vast and patient unfolds in the telling. The galaxy has existed for billions of years, and it will continue long after this night ends. Right now, you're safe, you're resting, and that's enough. You're floating high above the Milky Way's disk, looking down at a spiral of stars spread across the darkness like cream swirled into black coffee. From this impossible perspective, you can see the whole structure at once. A flat disk glowing pale blue and white near the center, spiral arms curving outward in graceful logarithmic curves, the entire shape rotating slowly around an invisible axis. The disk is thin compared to its width, like a coin balanced on edge in empty space, and if you could measure it, you'd find it stretches perhaps 1,000 light-years thick, but tens of thousands of light-years wide. This is home, the galaxy that holds your sun and every star you've ever seen with your naked eye, viewed from an angle no human has experienced except in imagination and mathematics. For most of human history, nobody knew the Milky Way had a shape at all. Ancient observers saw a pale river of light arcing across the night sky and invented stories to explain it. Spilled milk from a goddess, a road for spirits, a seam where the dome of heaven had been stitched together. They had no concept they were seeing the combined glow of billions of individual stars too distant to resolve. No idea they were living inside a disk and looking along its plane. When Galileo turned his telescope toward that pale band in 1610, he saw it dissolve into countless stars, but even he didn't understand the structure. It took 3 more centuries before astronomers confirmed the Milky Way was a rotating disk of stars, separate from other galaxies, one structure among countless others scattered through space. The confirmation came in the early 20th century through painstaking observation and measurement. Astronomers tracked stellar motions and found patterns suggesting rotation around a distant center. They discovered Cepheid variable stars in spiral nebulae and calculated distances, proving those nebulae were far outside the Milky Way, separate galaxies in their own right. Suddenly, the universe expanded from one system of stars to billions of galaxies, and humanity's cosmic address became just one disk among multitudes, an ordinary spiral in an ordinary region of space. The shift was profound, another step in the long demotion from the center of everything to nowhere in particular, but it opened astronomy to scales that had seemed unimaginable just decades before. Knowing the Milky Way was a galaxy didn't reveal its size, though. That required measuring distances to stars throughout the disk, mapping their positions in 3 dimensions, tracing where the spiral arms began and ended. Distance measurement became the central challenge, a problem that sounds straightforward, but proved extraordinarily difficult. You can't stretch a tape measure to a star thousands of light years away. You can't send a probe and clock the journey time. Instead, you have to rely on indirect methods, on patterns in starlight, on objects whose intrinsic properties you think you understand well enough to use as cosmic rulers. And every method carries assumptions, uncertainties, potential errors that can compound across vast distances. You're lying in your bed right now, the weight of your body pressing into the mattress, the pillow soft beneath your head. Maybe your eyes are closed, or maybe they're open but unfocused, staring at nothing in particular. The room is quiet except perhaps for your own breathing, for distant sounds from outside, for the subtle electronic hum of devices on standby. You don't need to memorize what comes next. Just let the story unfold like scenery passing outside a train window. Present but not demanding. There if you want to look, but fine if your attention drifts elsewhere. The galaxy exists whether you understand it or not. Right now, understanding is optional. Rest is what matters. The breakthrough in measuring cosmic distances came from a woman who spent her days examining glass photographic plates in a Harvard College observatory office. Henrietta Leavitt was hired as a computer, one of many women who did the tedious work of cataloging and measuring, while male astronomers took credit for the discoveries built on their labor. Leavitt studied variable stars, stars that brighten and dim in regular cycles, and she focused on those in the small Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere. Because all the stars in the cloud are roughly the same distance from Earth, she could compare their apparent brightnesses directly, and in that comparison, she noticed something remarkable. The brighter a Cepheid variable appeared, the longer its period of pulsation. This relationship, published in 1912, became one of the most important tools in astronomy. If you measured how long a Cepheid took to complete its cycle of brightening and dimming, you could calculate its true luminosity. And if you knew its true luminosity and measured how bright it appeared from Earth, simple geometry gave you the distance. It was a cosmic yardstick that worked across thousands and eventually millions of light years, a way to measure the universe that would underpin nearly every major distance calculation for the next century. Leavitt died in 1921. Her contributions often attributed to men who built on her work, but her discovery reshaped astronomy more profoundly than most Nobel Prize-winning research. Using Leavitt's method, astronomers in the 1920s began measuring distances throughout the Milky Way. They found Cepheid variables in star clusters, in regions of active star formation. In the spiral arms, they were beginning to map. Harlow Shapley used similar variable stars called RR Lyrae to measure distances to globular clusters, dense spheres of ancient stars orbiting the galaxy in a vast halo. His measurements revealed that these clusters weren't centered on the Sun, but on a point tens of thousands of light years away in the direction of Sagittarius. The realization proved the Sun was nowhere near the galaxy's center, that Earth occupied an ordinary position far out in the disk, another blow to humanity's lingering sense of cosmic importance. Shapley estimated the Milky Way was about 300,000 light-years across, a number that turned out to be roughly twice too large. His error came from multiple sources. He didn't fully account for interstellar dust dimming distant stars. His calibration of RR Lyrae luminosities was slightly off, and his definition of the galaxy's edge included structures others would later exclude. But his work proved the galaxy was vast and established the Sun's position far from the center, insights that survived even as his specific distance measurements were revised downward. Through the middle decades of the 20th century, those revisions converged on a value of about 100,000 light-years for the galaxy's diameter, a number that appeared in textbooks and became the standard answer anyone would give. That 100,000 light-year measurement seemed solid because multiple methods agreed on similar values. Radio observations of neutral hydrogen mapped the spiral arms and suggested a similar size. Optical surveys traced stellar populations across the disk and found density dropping steeply beyond 50,000 light-years radius. Different astronomers using different techniques got consistent results, and the consistency created confidence. But the agreement was misleading, because all the methods shared similar systematic errors. They all underestimated the effects of interstellar dust. They all relied on calibrations that would later be revised. They all struggled to see the faintest, most distant stars that traced the outer edge of the disk. The measurements matched not because they were correct, but because they were wrong in the same direction. The dust problem was particularly insidious. Interstellar space isn't empty, but filled with fine grains of carbon and silicate, concentrated along the plane of the galactic disk. These grains absorb and scatter starlight, making distant objects appear dimmer and redder than they actually are. Blue light, and with its shorter wavelength, scatters more than red, so stars seen through dust look redder than their true color, an effect called interstellar reddening. If you don't account for this reddening correctly, you underestimate how bright a star really is, and therefore you underestimate its distance. Early astronomers knew dust existed, but they drastically underestimated how much of it lay between them and the stars they were trying to measure. Robert Trumpler proved the widespread existence of interstellar extinction in 1930 by studying open star clusters at various distances. He measured their apparent sizes and brightnesses and noticed that distant clusters appeared smaller than nearby ones, even after accounting for distance. The only explanation was that the distant clusters were actually farther away than calculated, which meant something was dimming their light more than expected. Trumpler estimated dust absorption averaged about 1 magnitude per kiloparsec, a rough value that varied enormously depending on which direction you looked. Some lines of sight passed through dense molecular clouds where stars were completely obscured. Others were relatively clear, offering windows to greater distances. Without knowing exactly how much dust lay in each direction, distance measurements remained uncertain. You can feel your breathing now, steady and slow. The rise and fall of your chest as air moves in and out without conscious thought. The technical details might blur together. Words like magnitude and kiloparsec losing their edges, becoming sounds rather than meanings. That's completely fine. You're not here to master astronomical terminology. You're here to rest while someone tells you about people trying to measure something vast, making mistakes because their tools weren't good enough yet, gradually building better instruments and correcting errors. The story is about patience, about incremental progress, about the gap between what you can see and what's really there. And right now, you're just listening, just breathing, just being present while the story unfolds. What finally broke through the limitations of optical astronomy was observing the galaxy at wavelengths human eyes can't see. Radio astronomy, which developed rapidly after World War II, allowed astronomers to map the Milky Way using the 21-centimeter emission line of neutral hydrogen. Radio waves passed through dust as if it weren't there, so radio telescopes could see across the entire disk without obscuration. The first large-scale radio maps appeared in the 1950s and revealed the spiral structure clearly for the first time, showing arms that wound around the center in patterns similar to spirals photographed in other galaxies. The hydrogen gas extended beyond the edge of the optical disk, reaching perhaps 80,000 light-years from the galactic center, hinting the galaxy might be larger than optical observations suggested. Infrared astronomy proved even more important. Infrared light, with wavelengths longer than visible red, penetrates dust almost as effectively as radio, but reveals different structures, cool stars, regions of star formation shrouded in gas, populations of objects invisible to optical telescopes. Early infrared work was limited by atmospheric water vapor and by primitive detectors, but space-based missions transformed the field. NASA's Spitzer Space Telescope, launched in 2003, mapped the Milky Way in multiple infrared wavelengths and revealed structures that had been completely hidden. The galaxy's central bar appeared longer than optical observation suggested, extending about 27,000 light-years from end to end. The spiral arms reached farther out, traced by cool red stars invisible in visible light. The overall picture was of a galaxy more extensive than the textbook value implied. The real revolution came with the European Space Agency's Gaia mission, launched in 2013 with the goal of measuring positions, distances, and motions for over 1 billion stars. Gaia orbits at a gravitationally stable point called L2, 1.5 million kilometers from Earth, always staying aligned with the Earth-Sun line. From this position, the spacecraft slowly rotates, scanning the entire sky repeatedly, measuring each star's position dozens of times with extraordinary precision. The method relies on parallax, the apparent shift in a star's position when viewed from different locations as Earth orbits the Sun. Gaia's precision extends parallax measurements to tens of thousands of light-years. far enough to map most of the galactic disk with direct distance measurements, rather than relying on assumptions about stellar luminosity or corrections for dust. The first major data releases from Gaia came in 2016, 2018, and 2020 ICE, each containing positions and distances for hundreds of millions of stars. When astronomers analyzed the data, they found a galaxy more complex and extensive than earlier models suggested. The disk was warped, bending up on one side and down on the other. There were ripples and corrugations, waves in the stellar distribution caused by past collisions with satellite galaxies. And crucially, the stellar disk extended farther than the 100,000 light-year estimate, reaching out to perhaps 85,000 light-years from the galactic center in radius, which meant a total diameter approaching 170,000 light-years or more. The Milky Way was substantially larger than the textbooks had said for most of the 20th century, and the error had persisted simply because the tools to measure it correctly didn't exist until recently. You're standing inside an observatory dome on Mount Wilson in California, sometime in the 1920s. The air so cold, you can see your breath even though you're wearing layers of wool. The telescope rises above you, a massive tube of steel and glass pointing at a patch of sky, tracking stars as Earth rotates beneath them. The only light comes from dim red bulbs that won't ruin your night vision, and the only sounds are the quiet hum of the telescope's motor and the occasional creak of metal expanding and contracting in the mountain cold. This is where Edwin Hubble worked, where he discovered that spiral nebulae were actually distant galaxies, and where generations of astronomers spent freezing nights trying to measure the universe one photographic exposure at a time. The process was slow and demanded patience that feels almost incomprehensible now. You'd aim the telescope at a target, open the shutter on a glass photographic plate coated with light-sensitive emulsion, and let starlight accumulate for hours while the telescope tracked the sky's rotation. Longer exposures revealed fainter stars, but they also increased the risk of errors, a tracking mistake that blurred the image, vibrations from wind shaking the dome, fog rolling in and ruining everything. After hours of exposure, you'd close the shutter, carefully remove the glass plate, and carry it to a dark room where chemical developer would reveal the image under dim red safe light. Tiny dots would appear, each one a star whose light had traveled across space for years or centuries before landing on this particular piece of glass on this particular night. Then came days or weeks of measurement. You'd place the developed plate under a microscope and examine each star individually, measuring its position relative to reference marks etched into the glass, estimating its brightness by comparing the size of its image dot to a calibrated scale. The relationship between brightness and dot size wasn't perfectly linear and depended on exposure time, emulsion chemistry, development technique, even the temperature of the chemicals. Small errors crept in constantly. A magnitude estimate might be off by a few tenths. A position measurement might drift if the microscope wasn't perfectly focused. These small errors accumulated across thousands of measurements, introducing uncertainties that propagated through every calculation of distance and size. Interstellar dust compounded every difficulty. The Milky Way's disk is thick with microscopic grains of carbon and silicate, debris from dying stars, mixed with material left over from the galaxy's formation. These grains absorb and scatter starlight, and they do it preferentially. Blue light scatters more than red because its wavelength is shorter, comparable to the size of the dust grains themselves. The result is that stars viewed through dust appear both dimmer and redder than they actually are, an effect called interstellar reddening and extinction. If you measure a distant star's brightness and don't account for the dust between you and it, you'll think the star is intrinsically fainter than it really is, and therefore closer than it actually is. Your distance estimate will be wrong, systematically too small. Early astronomers knew dust existed because they could see dark nebulae silhouetted against bright star fields, regions where dust was so thick it blocked light completely. But they underestimated how much dust was distributed throughout seemingly empty space, how even clear regions of sky contained enough grains to dim distant stars by measurable amounts. The underestimate was natural given the tools available. Photographic plates weren't sensitive enough to detect subtle color shifts. Spectroscopy was too time-consuming to apply to large numbers of stars. The measurements that would have revealed the true extent of dust simply couldn't be made yet. So astronomers worked with incomplete information and made reasonable but ultimately incorrect assumptions about how transparent the galaxy was. You're back in your bed now, the observatory fading from imagination, and perhaps you're aware of how heavy your eyelids feel, how your thoughts are starting to drift in that particular way that happens before sleep, the warmth of the blanket around you, the softness of the pillow beneath your head, the way your body has settled into the mattress. All of it creates a kind of cocoon where the outside world feels distant and unimportant. You don't need to follow every technical detail. The story is really about people trying to measure something vast with tools that weren't quite good enough, making mistakes not from carelessness, but from the fundamental difficulty of the problem. Just let the words continue. Let them be a gentle current carrying you wherever your mind wants to go. Robert Trumpler's work in 1930 provided the first clear proof that interstellar dust was dimming starlight throughout the galaxy. He studied open star clusters, loose groups of young stars born together and drifting through space as a unit. By measuring the apparent sizes and brightnesses of clusters at various distances, Trumpler noticed something strange. Distant clusters appeared systematically smaller than nearby ones, even after accounting for perspective. The only way this made sense was if the distant clusters were farther away than his calculations indicated, which meant their light was being dimmed more than he'd assumed. Trumpler estimated that dust caused about 1 magnitude of extinction per kiloparsec, meaning stars appeared about 2.5 times dimmer for every 3,200 light-years you looked through the disk. This was an average value, though, and the reality was far patchier. Some directions passed through giant molecular clouds, where extinction reached dozens of magnitudes, enough to completely hide entire regions of the galaxy. Other directions were relatively clear, offering windows to greater distances. The variation meant you couldn't just apply a standard correction to every measurement. You had to estimate the dust along each specific line of sight, a task that required detailed observations of stellar colors and spectra. Different astronomers made different estimates, leading to disagreements about distances that sometimes differed by 20 or 30%. Those disagreements propagated into disagreements about the galaxy's size and structure, and resolving them required better data than photographic plates could provide. The breakthrough came from observing at wavelengths beyond what human eyes can detect. Radio astronomy opened the first new window. In 1951, Harold Ewan and Edward Purcell detected the 21-centimeter emission line of neutral hydrogen, radiation produced when a hydrogen atom's electron flips its spin state. This emission passes through dust clouds as if they weren't there, so radio telescopes could map hydrogen throughout the entire galaxy without worrying about extinction. By the mid-1950s, astronomers had used this technique to trace the spiral arms for the first time, showing that the Milky Way had a structure similar to other spiral galaxies photographed at optical wavelengths. The hydrogen disk extended to roughly 80,000 light-years from the galactic center, farther than the optical disk, but supporting the general picture of a galaxy about 100,000 light-years in diameter. Infrared astronomy proved even more transformative. Infrared light, with wavelengths between visible red and radio, penetrates dust almost as well as radio, but reveals different objects. Cool red giant stars, brown dwarfs, regions of star formation wrapped in cocoons of gas and dust. Early infrared work from the ground was difficult because Earth's atmosphere, especially water vapor, absorbs much of the infrared spectrum. Astronomers had to build telescopes on high-tech, dry mountaintops and use special detectors cooled to cryogenic temperatures to detect faint infrared sources against the warm glow of the telescope and atmosphere. Progress was slow through the 1960s and 70s, but each improvement revealed structures invisible to optical telescopes, hints that the galaxy contained more than optical surveys suggested. Space-based infrared observatories changed everything. NASA's Infrared Astronomical Satellite, IRAS, launched in 1983 and surveyed the entire sky in 4 infrared wavelengths, detecting hundreds of thousands of sources. The mission lasted only 10 months before its liquid helium coolant ran out, but the data revealed a galaxy rich in cool dust and hidden star formation. The Spitzer Space Telescope, launched in 2003 with more sensitive detectors and better spatial resolution, pushed infrared astronomy even further. Spitzer mapped the Milky Way's spiral structure in exquisite detail, showing that the central bar was longer than optical observations indicated, and that the spiral arms extended farther than previous estimates. The infrared view made it increasingly clear that defining the galaxy's size based solely on optical observations was missing a substantial fraction of the structure. But the real revolution came from Gaia's ability to measure distances directly rather than relying on assumptions about stellar luminosity. The spacecraft's method is elegantly simple in principle. Measure a star's position very precisely from opposite sides of Earth's orbit around the Sun. Note how much the star appears to shift against more distant background stars, and use basic trigonometry to calculate the distance. This is called parallax, and it's the most direct distance measurement method astronomy has. The challenge is that the shifts are incredibly tiny. Even for the nearest stars beyond the Sun, parallax shifts are less than 1 arcsecond, which is like measuring the width of a coin from several kilometers away. For stars across most of the galaxy, the shifts are measured in milliarcseconds or microarcseconds, requiring extraordinary precision. Gaia achieves that precision through obsessive attention to stability and calibration. The spacecraft's 2 telescopes are mounted on a rigid frame made of silicon carbide, a ceramic material that barely expands or contracts with temperature changes. The detectors are arranged in a grid that measures star positions to a fraction of a pixel. The entire spacecraft rotates slowly, scanning the sky in strips, and sophisticated software tracks each star's motion through the field of view. Over 5 years of observations, most stars were measured dozens of times, allowing Gaia to average out random errors and detect systematic problems in the measurements. The final catalogue contains positions accurate to microarcseconds for hundreds of millions of stars. Distance is accurate to a few percent for millions of stars within several thousand light-years, and useful parallax measurements extending to tens of thousands of light-years. When astronomers analyzed Gaia's data releases, the picture that emerged was of a galaxy more complex and more extensive than simple models suggested. The stellar disk didn't end cleanly at some well-defined radius. Instead, it faded gradually, with stellar density declining steadily as you moved outward from the center, but never quite dropping to zero. Trace the density curve far enough, and you'd still find stars at 80,000 or 90,000, even 100,000 light-years from the galactic center. Where exactly you drew the boundary depended on what threshold you chose. If you said the disk ended where stellar density dropped below 1% of its value in the solar neighborhood, you got one number. If you chose a different threshold, you got a different number. But no matter which reasonable definition you used, the answer came out larger than the traditional 100,000 light-years. You're still here, breathing slowly, and maybe you've lost track of some of the technical details, the specific numbers and mission names blurring together. That's not just okay, it's expected. The point isn't to memorize facts, but to understand the shape of the story, a measurement that seemed solid, tools that weren't quite good enough, dust that hid the truth, and finally, new instruments that revealed what had been there all along. The galaxy didn't change, only the knowing changed. And that knowing continues to evolve as more data accumulates, as methods improve, as the map gets refined. Tonight, you're just resting here while someone tells you about that process, about humans slowly figuring out how large their cosmic home really is. You're floating near the edge of the Milky Way's visible disk now, looking back toward the center from a distance of perhaps 70,000 light-years. From here, the galaxy appears as a bright band across the sky, not unlike how it looks from Earth, but wider, encompassing more of your field of view. The spiral arms are visible as slightly brighter regions, lanes of blue light marking where young massive stars are forming, and between the arms are darker gaps where older, redder stars drift in quieter orbits. The whole structure is thin, impossibly thin for something so vast, like a layer of frost spread across a window. If you were standing on a planet here at the edge, the night sky would be darker than Earth's, with fewer stars visible to the naked eye, and the Milky Way's band would arc across the heavens like a glowing bridge leading inward toward the crowded center. Measuring the galaxy's size from Earth is fundamentally a problem of perspective. You're trying to map a structure while embedded inside it, like trying to draw a floor plan of a house while standing in one of the rooms. Every direction you look, your view passes through layers of stars and dust and gas, and separating foreground from background becomes an exercise in careful analysis and statistical inference. Stars that appear close together in the sky might be at vastly different distances, separated by thousands of light-years, but aligned by chance along the same line of sight. To build a three-dimensional map from two-dimensional observations requires measuring distance to each star individually, a task that seemed almost impossible before modern instruments made it feasible. The traditional approach used what astronomers call standard candles, objects whose intrinsic brightness you think you know. Cepheid variables are standard candles because their pulsation period tells you their luminosity. If you measure how bright a Cepheid appears from Earth, and you know its true luminosity, basic physics gives you the distance. Apparent brightness falls off as the square of distance, so a star that appears 4 times dimmer is twice as far away. The method works beautifully in principle, but it depends on your calibration being correct. If you've slightly misjudged how luminous Cepheids really are, all your distance measurements will be systematically wrong, and you won't necessarily know it because all your measurements will be wrong in the same consistent way. That's exactly what happened with early distance measurements in the Milky Way. The calibration of Cepheid luminosities was based on measurements to nearby star clusters and to the Magellanic Clouds, and those measurements themselves were affected by dust extinction that wasn't fully accounted for. The result was that Cepheid luminosities were slightly underestimated, which meant distances calculated using Cepheids were slightly underestimated, which meant the galaxy appeared smaller than it really was. The error wasn't enormous, maybe 20 or 30%, but it was consistent and systematic. When multiple astronomers used the same method with the same calibration, they all got similar results, and the agreement looked like confirmation that they were right. It took decades and better data to reveal the calibration itself was flawed. You're lying in bed, and the blanket has warmed to body temperature now, holding heat close to your skin while the room beyond stays cool. Maybe you're aware of the weight of the fabric, the slight pressure against your chest and legs, or maybe your attention has drifted elsewhere, to sounds from outside or to thoughts that have nothing to do with astronomy. Both are fine. You don't have to stay focused. The story continues whether you're following every word or letting most of it wash past as texture and rhythm. The galaxy rotates above you in its billion-year cycles, patient and indifferent to whether anyone measures it correctly. Right now, in this moment, the only thing that matters is that you're comfortable, that you're safe, that sleep will come when it's ready. Another challenge in measuring the galaxy's size is defining what you mean by size. Do you count only the bright disk, where most star formation happens? Do you include the halo of old stars and globular clusters that extends far above and below the disk? What about the dark matter halo, the invisible sphere of mass that extends perhaps 1 million light-years from the center and holds satellite galaxies in orbit? Different definitions give wildly different answers. The bright stellar disk is roughly 170,000 light-years across, based on recent measurements. The halo of globular clusters extends to perhaps 500,000 light-years. The dark matter halo might reach twice that far. Which number represents the galaxy's true size depends on what you're trying to measure and why. For most of the 20th century, astronomers focused on the stellar disk because that's what they could observe most easily. Stars emit light, making them detectable with telescopes. Gas can be detected in radio and infrared wavelengths, but dark matter doesn't emit or absorb light at any wavelength, making it effectively invisible except through its gravitational effects. You can infer dark matter's presence by watching how stars and gas move, by measuring rotation curves that stay flat far beyond where visible matter trails off, by tracking the orbits of satellite galaxies. These observations prove dark matter exists and dominates the galaxy's total mass. But they don't help you see the disk's edge or map, where stars give way to empty space. The disk itself is not uniform. It has structure, a thin disk where most stars orbit in nearly circular paths close to the galactic plane, a thick disk of older stars with more tilted and elliptical orbits, and a central bulge where stars crowd densely around the galactic center. The thin disk is where spiral arms appear most prominently, where gas clouds collapse to form new stars, where the youngest and brightest objects are found. The thick disk contains older stars, perhaps 10 billion years old, stars that formed when the galaxy was younger and more chaotic. The bulge is dominated by even older stars, some of the galaxy's first generation, moving in complex orbits shaped by the central supermassive black hole's gravity and by the elongated bar structure that funnels gas toward the center. Gaia's data revealed that these components blend together rather than separating cleanly. There's no sharp boundary between thin disk and thick disk, just a gradual change in the properties of stellar populations as you move away from the galactic plane. The warp in the outer disk means that even defining the plane becomes ambiguous beyond a certain radius. In the solar neighborhood, about 27,000 light-years from the center, the disk is relatively flat, and the distinction between thin and thick disks is clear. But farther out, the disk bends and twists. Stars have more random motions, and the neat categories start to break down. Measuring the size requires choosing some threshold for where the disk becomes too sparse or too disordered to count, and that choice inevitably introduces some arbitrariness into the answer. One of the most striking findings from Gaia was the discovery of ripples in the stellar disk, vertical waves that propagate outward from the galactic plane like corrugations in cardboard. These ripples are thought to be caused by gravitational interactions with the Sagittarius dwarf galaxy. a small galaxy currently being torn apart as it passes through the Milky Way's disk. Each time Sagittarius crosses the disk, its gravity tugs on stars, setting up oscillations that persist for hundreds of millions of years. The ripples are subtle, with amplitudes of just a few hundred light-years, but they're detectable in Gaia's precise position measurements. They're a reminder that the galaxy is not static, that its structure is constantly being disturbed by interactions with smaller galaxies falling in from the halo, merging and dissolving, and leaving trails of stars that slowly mix into the larger population. These tidal streams from disrupted galaxies provide another way to probe the galaxy's extent. When a small galaxy falls into the Milky Way, tidal forces stretch it into a long stream of stars that wraps around the larger galaxy. By mapping these streams and measuring their orbits, astronomers can trace the gravitational field far from the galactic center, revealing how mass is distributed in regions where individual stars are too sparse to observe directly. Gaia has detected dozens of such streams, some from galaxies that merged billions of years ago, others from galaxies being disrupted right now. The streams extend to hundreds of thousands of light-years, far beyond the visible disk, and they show that the Milky Way's gravitational influence reaches much farther than the region where most stars live. You might notice your thoughts drifting now, the technical language fading into a kind of gentle static, present but not demanding attention. That's the right way to listen to this. Let the images come and go without trying to hold them. A warped disk bending through space, ripples propagating outward from gravitational disturbances, streams of stars tracing ancient collisions. None of it requires effort to understand completely. The galaxy's complexity is vast, its history layered across billions of years, and tonight you're just touching the surface, letting a few ideas settle lightly before sleep comes. The details don't matter as much as the feeling that the universe is larger and stranger and more patient than human timescales can fully grasp. The question of the galaxy's size connects to deeper questions about how it formed and evolved. Current models suggest the Milky Way grew through hierarchical merging, with small proto-galaxies colliding and combining over billions of years to build the structure we see today. The oldest stars, found in the halo and the bulge, formed in these early building blocks before they merged. The disk assembled later as gas settled into a rotating plane and formed stars in situ. Recent mergers, like the ongoing disruption of the Sagittarius dwarf, continue to add mass and disturb the disk. Understanding the galaxy's current size helps astronomers reconstruct this history, helps them figure out how many mergers contributed what fraction of the total mass, helps them compare the Milky Way to other galaxies and understand whether its history was typical or unusual. The size also matters for understanding the galaxy's future. In about 4 billion years, the Milky Way and the Andromeda galaxy will collide, a slow-motion merger that will scramble both galaxies' structures and eventually form a single larger elliptical galaxy. Whether the Milky Way survives as a distinct disk during the initial pass depends partly on its current size and mass distribution. A larger, more massive disk would be more resilient to tidal disruption. The merger will also bring Andromeda's satellite galaxies into the system, adding more small galaxies to the mix, more streams to unravel, more complexity to the final structure. Knowing the Milky Way's size today gives astronomers a baseline for modeling what comes next, for predicting how the local universe will evolve over time, scales far longer than humans will exist to witness. As your breathing slows and deepens, as the boundary between waking and sleeping becomes softer, hold this thought. The galaxy is larger than the books said, and the era lasted nearly a century because measuring vast things from the inside is genuinely hard. But humans kept building better instruments, kept refining methods, kept checking and correcting, and gradually the map expanded to match the reality that was there all along. The Milky Way didn't wait for human understanding. It simply existed, vast and patient, while tiny observers on one small world worked out how to see it clearly. And now, tonight, you've been part of that story, even if only as a listener drifting towards sleep, while the measurements continue far above, unchanging and immense. You're sitting in a university office sometime in the 1950s, papers spread across a desk, a mechanical calculator clicking as you work through equations. Outside the window, students cross a quad under autumn trees, but you're focused on columns of numbers. Stellar magnitudes, color indices, distance estimates for star clusters scattered throughout the galactic disk. You're trying to reconcile measurements from different methods, and they don't quite agree. Cepheid distances suggest one value. Spectroscopic parallax gives something slightly different. Cluster main sequence fitting yields a third number. The discrepancies are small, just 10 or 15% say, but they matter when you're trying to draw a definitive map. You suspect dust is the culprit, but you don't have a way to measure it accurately for each individual star, so you're making educated guesses, hoping the errors average out. This was the reality of mid-century astronomy, painstaking calculations done by hand or with primitive computers, data that never quite lined up perfectly, systematic uncertainties you couldn't eliminate because the tools didn't exist yet. Astronomers knew their measurements had errors, but they often couldn't tell which measurements were wrong or by how much. The standard approach was to average multiple methods, hoping the truth lay somewhere in the middle. But if all the methods shared the same systematic bias, the average would be wrong too. That's what happened with the galaxy's size. Every method underestimated distances because of dust, so the average of all methods was also too small. And the error persisted because everyone was making the same mistake. The dust problem was particularly vicious because it wasn't uniform. Some regions of the galaxy are relatively clear, with just a thin haze of grains between stars. Other regions contain dense molecular clouds, vast structures where gas and dust are so thick they block visible light completely. These clouds show up as dark patches in photographs of the Milky Way, silhouetted against the background glow of more distant stars. The largest, like the Coalsack Nebula visible from the southern hemisphere, span tens of light years and contain enough mass to form thousands of stars. When your line of sight passes through one of these clouds, extinction can reach dozens of magnitudes, making stars behind the cloud effectively invisible at optical wavelengths. But even in directions that appear clear, there's still dust. It's distributed throughout the disk in a layer perhaps 300 light-years thick, denser near the plane and thinning out above and below. This diffuse dust doesn't block light completely, but dims it gradually. A few tenths of a magnitude per 1,000 light-years, enough to add up over the large distances involved in mapping the galaxy. Early astronomers developed empirical corrections based on the observed reddening of stars' eye, using the fact that dust makes stars appear redder to estimate how much extinction had occurred. But the relationship between reddening and extinction depends on the properties of the dust grains, which vary from region to region. Grains near regions of star formation are different from grains in the diffuse interstellar medium. The corrections were approximate at best. You're lying in bed now and maybe you've pulled the blanket higher, tucking it under your chin, feeling the weight settle across your shoulders. The room is dark or nearly so, just faint light from a street lamp outside or the glow of a phone charging somewhere nearby. Your body has found its position, the one it settles into naturally, and moving would require effort you don't want to spend. The story continues in your ears, words arriving one after another, and you don't have to do anything with them. They're just there, like rain on a roof, a pattern of sound that doesn't demand response. If you fall asleep before the story ends, that's not failure. That's exactly what this is for. One of the things that makes measuring the galaxy difficult is that different stellar populations trace different structures. Young massive stars, the bright blue ones that live only a few million years, are found exclusively in the spiral arms and regions of active star formation. These stars are easy to see because they're luminous, but they don't tell you much about the overall mass distribution because they represent only a tiny fraction of stars by number. Old red stars, which make up the bulk of the stellar population, are much fainter and harder to detect, especially at large distances. Brown dwarfs, objects too small to sustain hydrogen fusion, are fainter still and require infrared observations to detect at all. If you map the galaxy using only bright young stars, you get a different picture than if you map it using the full population. This selection effect influenced early estimates of the galaxy's size. Optical surveys naturally emphasized bright stars because those were easiest to observe, and bright stars are concentrated in the spiral arms and the inner disk. The faint old stars in the outer disk were largely missed, not because astronomers weren't looking for them, but because the photographic plates and instruments of the time couldn't detect them at those distances. It's like trying to count all the people in a city at night by looking for lit windows. You'll find concentrations in downtown areas and miss the suburbs entirely. Not because the suburbs are empty, but because they're harder to see. The galaxy's true extent remained hidden until infrared and space-based surveys could detect the faint populations that traced the outer disk. Radio observations provided a complementary view. The 21-centimeter line of neutral hydrogen traces gas, rather than stars. But gas and stars are related. Stars form from gas, and dying stars return material to the interstellar medium. So regions with gas often have stars nearby. Radio maps showed hydrogen extending well beyond the optical disk, reaching 70 or 80,000 light-years from the galactic center. But gas is more loosely bound than stars, easier to disturb by interactions with satellite galaxies or by pressure from the intergalactic medium. Some astronomers argued the gas disk shouldn't define the galaxy's size because it wasn't a stable, long-lived structure in the same way the stellar disk was. Others countered that gas is part of the galaxy too, that excluding it was arbitrary. The debate reflected genuine ambiguity about what counts as the galaxy versus what counts as its extended environment. Infrared surveys began to resolve this ambiguity by detecting stellar populations invisible to optical telescopes. The 2-micron all-sky survey, completed in 2003, judges catalogued over 300 million stars in near-infrared wavelengths. The survey revealed red giants and cool main sequence stars throughout the disk, including in regions that appeared nearly empty in optical images. These stars are old, often several billion years old, and they orbit the galaxy in nearly circular paths like the Sun does. They're not part of a transient population that will disperse after a few million years. They're permanent residents of the disk, and their presence at large radii meant the disk itself extended farther than optical surveys suggested. Spitzer's observations pushed even deeper into the infrared, detecting stars and dust at wavelengths where the galaxy looks completely different from familiar optical images. At these wavelengths, the central bulge glows intensely, dominated by cool red giants crowded around the galactic center. The spiral arms stand out not as lanes of bright blue stars, but as regions where warm dust glows from being heated by young stars. The bar structure at the galaxy's center appears clearly, extending about 13,000 light-years on either side of the core, much longer than optical observations suggested. All of this infrared structure contributed to the realization that the galaxy was more extensive, than the 100,000 light-year estimate implied. But even with infrared surveys and Gaia's parallax measurements, defining the galaxy's exact size remains somewhat arbitrary. The stellar density doesn't drop suddenly to zero at some well-defined radius. Instead, it declines gradually. Following what astronomers call an exponential profile, the density decreases by a constant factor for every kiloparsec you move outward. You can trace this profile out to very large radii, and depending on where you decide the density has become negligibly small, you'll get different estimates for the size. Most recent studies place the stellar disk's effective radius at around 85,000 light-years, meaning the total diameter is roughly 170,000 light-years. But this is based on defining the edge as the point where stellar density drops below some threshold, typically 1% of the solar neighborhood value. If you used a different threshold, you'd get a different number. Use 0.5% and the disk appears larger. Use 2% and it appears smaller. The ambiguity isn't a flaw in the measurements, it's a fundamental feature of the structure being measured. Galaxies don't have sharp edges. They fade gradually into the surrounding space, and the choice of where to draw the boundary is somewhat subjective. What matters more than the exact number is that modern measurements, regardless of which threshold you choose, consistently give values significantly larger than the traditional 100,000 light-years. The galaxy is bigger than textbooks said for most of the 20th century, not by a small margin, but by tens of thousands of light-years, enough to matter for understanding its mass, its structure, and its place among other galaxies. You can feel sleep approaching now, maybe, or maybe you're still alert but deeply relaxed, mind quiet but present. Either state is fine. The story is winding through its middle sections, exploring details and complications, showing how scientific knowledge develops through slow accumulation of better data rather than sudden revelations. There's something calming about that pace, about understanding that getting things right takes time, that errors are part of the process, that each generation builds on what came before, even if some of what came before turns out to be slightly wrong. The galaxy waits patiently while humans figure it out, spinning in its slow, inexorable rotation, indifferent to whether any particular measurement is accurate or not. The realization that the Milky Way is larger than long believed has implications beyond just updating a number in textbooks. The galaxy's size connects to its total mass, to how much dark matter it contains, to how its rotation curve behaves in the outer regions. A larger disk means more stars, which means higher stellar mass, which affects estimates of the star formation rate and the chemical evolution history. It also affects comparisons with other galaxies. The Milky Way is often described as a typical large spiral galaxy, but typical compared to what? If we've been underestimating its size, maybe it's actually more massive or more luminous than we thought, which would change where it fits in the distribution of galaxy properties. These questions ripple outward, affecting multiple areas of research, showing how a single measurement connects to a web of related questions. As your thoughts drift and fragment, as the words become texture rather than meaning, let yourself rest in the knowledge that the universe is large and patient and will still be here tomorrow. The Milky Way rotates above you, a structure so vast it takes light 170,000 years to cross from edge to edge, and you're embedded in it, a temporary pattern of atoms arranged briefly into consciousness before dispersing back into the cycle of cosmic recycling. Tonight you've learned that even the most basic facts about this structure can be wrong for decades, that knowledge is always provisional, always open to revision, and that's okay. That's how understanding grows, slowly and carefully, building toward truth without ever quite reaching perfect certainty. You're aboard the Gaia spacecraft now, floating at the Lagrange point L2, 1.5 million kilometers from Earth, always positioned on the opposite side of Earth from the Sun. From here, Earth appears as a bright blue dot, the Moon a smaller companion, both drifting together against the blackness. The spacecraft itself is small, roughly the size of a car, but it carries instruments capable of measuring the positions of stars with precision that seems almost absurd, micro-arc seconds, which is like measuring the width of a human hair from the distance between continents. The spacecraft rotates slowly, once every 6 hours, sweeping 2 telescopes across the sky in a pattern that gradually covers the entire celestial sphere. Every star that passes through the field of view is recorded, measured, catalogued, and over months and years, these measurements accumulate into a 3-dimensional map of unprecedented detail. The engineering required to achieve this precision is extraordinary. The spacecraft's structure is made of silicon carbide, a ceramic material chosen because it barely expands or contracts with temperature changes. Even a microscopic shift in the distance between the 2 telescopes would ruin the measurements, so the structure has to be thermally stable to within microns. The mirrors are polished to near perfect smoothness, free of defects that would scatter light and blur star images. The detectors, arrays of CCDs similar to what's in a digital camera, but far more sensitive, are calibrated obsessively, with corrections for every tiny imperfection in how individual pixels respond to light. The spacecraft's pointing is controlled to millisecond precision, compensating for the pressure of sunlight hitting the solar panels, for thermal expansion as components heat and cool, for the tiny gravitational tugs from Earth and Moon and Sun. Processing Gaia's data required building new software pipelines and algorithms. The raw measurements come down as positions of stars relative to each other, but to turn those into a catalogue of absolute positions and distances, you need to solve a massive optimization problem involving billions of measurements and millions of unknowns. Different stars appear in different observations, overlapping in complex patterns, and the spacecraft's attitude and calibration drift slightly over time. The solution requires iterative refinement, starting with approximate positions and gradually improving them as more observations accumulate. European teams worked for years developing these pipelines, testing them on simulated data, refining them as real data arrived. The first data release in 2016 was impressive, but incomplete. Each subsequent release improved calibrations, added more stars, pushed parallax measurements to fainter and more distant objects. What emerged from all this effort was a map showing the Milky Way in motion. Gaia didn't just measure where stars are now, but how they're moving. Their velocities across the sky and toward or away from us. These motions revealed streams of stars from disrupted satellite galaxies, groups of stars born together and still drifting as cohorts, regions where stellar orbits are disturbed by gravitational interactions. The data showed that the galaxy is not a static structure but a dynamic one, constantly evolving, shaped by ongoing collisions and the slow drift of stars through gravitational potential wells. And crucially, the data extended far enough to map the outer disk directly, to measure stellar positions at 70 or 80,000 light-years from the center, proving the disk reached farther than the traditional 100,000 light-year diameter suggested. You're lying in bed, and perhaps you've adjusted position slightly, rolled onto your side, pulled your knees up a little. The pillow has molded to the shape of your head, and the blanket drapes across your body in gentle folds. Maybe your eyes are closed now, or maybe they're open but seeing nothing in particular, just darkness and vague shapes. The story continues, but it's becoming harder to follow the thread, words arriving without quite forming complete thoughts. That's fine. You don't need to understand. The spacecraft orbits, the data accumulates, the map grows more detailed, and none of it requires your attention. Sleep is approaching, or maybe already here in patches, moments where consciousness fades and then returns, and you're safe in that border country between waking and dreaming. One of the most important findings from Gaia was the discovery that the Milky Way's disk is warped, bent like a vinyl record left too long in sunlight. Astronomers had suspected this from earlier radio observations of hydrogen gas, but Gaia's stellar measurements proved it definitively and showed the warp's structure in detail. The disk is flat near the Sun's position, about 27,000 light-years from the center, but farther out it bends progressively upward on one side of the galaxy and downward on the other. The warp's amplitude increases with distance, reaching perhaps several thousand light-years above or below the nominal plane at the disk's edge. The structure isn't static, but precesses slowly around the galaxy, taking several 100 million years to complete one cycle. The warp is thought to be caused by gravitational interactions with the Large and Small Magellanic Clouds, two dwarf galaxies that orbit the Milky Way and periodically pass close to the disk. When a small galaxy passes nearby, its gravity tugs on the outer disk, where stars are loosely bound and easily disturbed. The result is a bending wave that propagates through the disk like a ripple on a pond. The warp affects how we measure the galaxy's size because it means the disk doesn't have a well-defined single plane beyond a certain radius. Instead, it becomes a three-dimensional structure, twisted and bent, and defining where it ends becomes even more ambiguous than if it were perfectly flat. Gaia also revealed numerous stellar streams, narrow bands of stars stretched around the galaxy like ribbons. These streams are the remnants of small galaxies and star clusters that wandered too close to the Milky Way and were torn apart by tidal forces. As a small galaxy falls into the Milky Way, the side closer to the galactic center feels stronger gravity than the side farther out, and this difference stretches the galaxy into a long, thin stream. The stars in the stream continue orbiting the Milky Way, gradually spreading out and mixing with the background population. But for millions or even billions of years, the stream remains detectable as an overdensity of stars with similar motions and chemical compositions. By tracing these streams, astronomers can reconstruct the Milky Way's merger history, figuring out which small galaxies contributed what fraction of mass and when the mergers occurred. The most prominent stream visible in Gaia's data is from the Sagittarius dwarf galaxy, which is currently being disrupted as it passes through the Milky Way's disk for perhaps the third or fourth time. The Sagittarius stream wraps around the entire galaxy, extending from one side of the sky to the other, containing millions of stars spread over hundreds of thousands of light-years. Other streams are smaller and fainter, some from globular clusters that dissolved over billions of years, others from dwarf galaxies that merged in the distant past. Each stream tells part of the story of how the Milky Way grew to its current size, accreting smaller galaxies over cosmic time, building up mass through hierarchical merging rather than forming all at once. Understanding the galaxy's merger history helps explain why early size estimates were too small. If the Milky Way grew primarily through mergers, then its outer regions are made up of stars accreted from infalling satellites, stars that formed in other galaxies and only recently became part of the Milky Way. These accreted stars have different chemical compositions and orbital properties from stars that formed in the Milky Way's disk, and they're distributed differently in space. Early surveys that focused on disk stars naturally missed much of the accreted population, leading to underestimates of the total extent. Only when surveys became deep enough to detect faint stars throughout the halo did the full structure become apparent, revealing a galaxy larger and more complex than simpler models suggested. The question of the galaxy's size connects ultimately to the question of what a galaxy is. Is it just the bright disk where most stars live? Is it the entire gravitationally bound system, including the halo and satellite galaxies? Does it extend to wherever the Milky Way's gravity dominates over the gravity of neighboring galaxies? These aren't just semantic questions. They reflect genuine ambiguity about how to draw boundaries in systems that fade gradually rather than ending sharply. The Milky Way's stellar disk reaches to roughly 85,000 light-years radius, but the dark matter halo extends perhaps 10 times farther, and the gravitational influence reaches even beyond that. Which radius defines the galaxy depends on what you're trying to measure and why, and different answers serve different purposes. As your mind drifts further into that soft state between thoughts, where words arrive but don't quite form meanings, where images dissolve as quickly as they appear, you might hold one last idea before sleep takes over completely. The galaxy is vast and ancient and patient, and it doesn't mind that humans took a century to measure it correctly. The error wasn't important to the galaxy itself, only to the people trying to understand their place within it. And now the measurement has been corrected, the map redrawn, the number updated in papers and databases, and the slow work of science continues, refining and checking and occasionally discovering that something everyone believed for decades turns out to have been slightly wrong all along. You're standing in the control room at the European Space Operations Center in Darmstadt, Germany, watching data stream in from Gaia on monitors that glow softly in the dimmed room. Engineers sit at consoles, monitoring the spacecraft's health, checking that solar panels are generating power, that reaction wheels are maintaining attitude, that the instruments are operating within nominal parameters. The data arrives continuously, a river of numbers representing stellar positions measured to absurd precision, and it flows into storage systems where it will wait for processing pipelines to convert raw measurements into the catalog that astronomers around the world are waiting for. This is the unglamorous side of astronomy, the patient monitoring and data management that happens between the dramatic moments of discovery, the infrastructure that makes science possible even though it rarely appears in headlines. The challenge of measuring the galaxy's size isn't just about building better instruments. It's also about understanding the systematic errors that can hide in your data, waiting to bias your conclusions in ways you might not notice until someone else points them out decades later. Gaia's team spent years characterizing these systematics, identifying effects like how the spacecraft's temperature affects the distance between its two telescopes, how scattered light from bright stars can contaminate measurements of nearby faint stars, how the detector pixels don't all respond exactly the same way to incoming photons. Each effect needed to be modeled and corrected, and some effects were only discovered after analyzing real data and noticing patterns that didn't match expectations. One particularly subtle systematic involved something called basic angle variation. Gaia's two telescopes are mounted on a rigid frame separated by a precise angle, and the whole measurement scheme depends on that angle being constant. But even silicon carbide isn't perfectly stable. Tiny temperature variations cause microscopic expansions and contractions, changing the angle between the telescopes by microarc seconds. These variations had to be monitored constantly using an onboard metrology system, a laser interferometer that measures the distance between reference points on the structure. The measurements fed into the calibration pipeline, correcting each observation for the angle variation that occurred at that moment. Without this correction, distances would be systematically wrong, and the error would grow with distance, exactly the kind of bias that could make the galaxy appear smaller or larger than it really is. These technical details might seem obscure, but they matter because they show how difficult it is to measure anything to high precision. Every instrument has limitations, every measurement has uncertainties, And sometimes those uncertainties don't become apparent until you've collected enough data to reveal patterns. The history of astronomy is full of examples where systematic errors led entire communities astray for years or decades. The galaxy's size is just one example. Another is the measurement of the Hubble constant, which determines how fast the universe is expanding. Different methods gave different values for decades, and only recently have astronomers begun to understand why, tracing the discrepancies to subtle calibration issues and unrecognized systematic effects in the data. You're lying in bed, and maybe you're aware of your body now only as a vague presence, weight distributed across the mattress, warmth held close by the blanket. Your breathing has slowed to the rhythm of deep rest, and your thoughts, if they're still forming coherently at all, drift without direction. The story continues in the background, words arriving steadily but no longer demanding attention, just texture and rhythm and the occasional phrase that surfaces briefly before dissolving. This is the right state for listening to this kind of thing, present but not focused, aware but not actively processing, letting the information wash through without trying to hold on to it. Beyond the technical challenges of measurement, there's a conceptual challenge. The galaxy doesn't have a sharp edge, so any size measurement requires choosing where to draw the boundary. Different researchers make different choices, and this contributes to the spread in published values. Some studies define the edge as the radius containing 90% of the stellar light. Others use the point where stellar density drops below some threshold. Still others look for the radius where the rotation curve begins to decline, indicating you've moved beyond the region where most of the mass is concentrated. Each definition is reasonable for certain purposes, but they give different answers, typically varying by 10 or 20,000 light-years. The important point is that all these definitions yield values larger than the traditional 100,000 light-years, confirming that the old estimate was too small, regardless of exactly which boundary definition you prefer. The galaxy's spiral arms add another layer of complexity to the size question. Spiral arms aren't permanent structures made of the same stars over time. They're density waves, regions where stars and gas bunch up temporarily as they orbit through the galaxy. Think of a traffic jam on a highway. The jam moves along the road even though individual cars pass through it and exit out the other side. Similarly, stars drift into a spiral arm, slow down slightly as they pass through the denser region, then drift out the other side. But the arm itself persists as a pattern rotating around the galaxy. The arms are traced by young bright stars because those stars form from gas clouds compressed as they enter the arm. But the arms themselves extend farther than the bright stars suggest, traced by older stars and by gas not yet forming stars. Mapping the spiral structure has been difficult because we're embedded in the disk, looking through layers of stars and dust that obscure the view. Different studies have proposed different numbers of major arms, 2, 4, or somewhere in between, and different patterns of how they wind around the center. Recent work combining Gaia's parallaxes with observations of young stars and gas clouds suggests the Milky Way has 4 major spiral arms, plus several shorter spurs, and these structures extend to at least 70,000 light-years from the galactic center, possibly farther. The uncertainty reflects the genuine difficulty of mapping structure from the inside, where perspective effects and dust extinction make it hard to distinguish features at different distances along the same line of sight. The central bar also affects measurements of the galaxy's size and shape. Bars are common in spiral galaxies, elongated structures at the center from which the spiral arms emerge. The Milky Way's bar is about 27,000 light-years long from end to end and rotates faster than the disk around it, completing one rotation every 200 million years compared to the Sun's orbit of 230 million years. Gas flowing along the bar gets funneled toward the center, fueling star formation and feeding the supermassive black hole. The bar's presence affects how mass is distributed in the inner galaxy, which influences the rotation curve, which connects to how you interpret measurements of the outer disk. Understanding the bar's size and orientation is crucial for building accurate models of the galaxy's structure and dynamics. One of the surprising discoveries from combining Gaia data with other surveys was that the stellar disk shows evidence of recent disturbances, ripples and waves that suggest something passed through relatively recently and stirred things up. The leading candidate is the Sagittarius dwarf galaxy, which is currently being disrupted as it passes through the Milky Way's disk. Computer simulations show that a small galaxy passing through the disk can set up oscillations that persist for hundreds of millions of years, causing stars to move up and down perpendicular to the disk in coordinated waves. Gaia detected exactly this kind of pattern, with stellar velocities showing coherent vertical motions that match predictions from Sagittarius impact simulations. The discovery suggests the Milky Way's disk is not in equilibrium, but still ringing like a bell from impacts that occurred hundreds of millions of years ago. These disturbances complicate the measurement of the disk's size and shape because they mean the structure isn't static. The disk is bending, warping, rippling in response to ongoing gravitational interactions, and the position of the edge shifts slightly depending on where you measure and when. Over millions of years, these disturbances will damp out and the disk will settle back toward equilibrium. But right now, we're catching the galaxy in a moment of dynamic evolution. That's actually typical for galaxies. Most are not perfect, settled structures, but works in progress, shaped by ongoing collisions and interactions that continue throughout cosmic time. The Milky Way appears calm on human timescales, but on galactic timescales, it's a dynamic, evolving system constantly being disturbed and responding to those disturbances. As sleep draws closer, as the boundary between hearing and not hearing becomes fuzzy and uncertain, let the story fade into background texture. The galaxy rotates slowly above you, indifferent to measurement, vast beyond easy comprehension. Humans spent a century getting its size wrong, then built better instruments and corrected the error, and the work continues, refining and checking, because that's how knowledge grows. You don't need to remember any of this tomorrow. You just needed something calm and vast to occupy your mind, while your body found its way toward rest. And now, whether you're asleep or nearly there or still drifting in that in-between state, you're safe, you're comfortable, and the night continues its patient march toward morning. You're floating in the halo now, far above the Milky Way's disk, looking down at the spiral from a distance of perhaps 200,000 light-years. From here, the disk appears small, a pale, glowing spiral surrounded by darkness, and scattered around it like fireflies are the globular clusters, dense spheres of ancient stars that orbit in the vast space above and below the disk. There are about 150 of these clusters orbiting the Milky Way, each containing hundreds of thousands to millions of stars, and they're among the oldest objects in the galaxy, formed over 12 billion years ago when the universe was less than 2 billion years old. These clusters trace the galaxy's dark matter halo, the invisible sphere of mass that extends far beyond the visible disk and holds everything together with its gravity. The globular clusters were crucial to Harlow Shapley's work in the 1910s, when he used them to prove the sun wasn't at the galaxy's center. By measuring distances to dozens of clusters, using RR-Lyrae variable stars, Shapley showed that the clusters were centered on a distant point in the direction of Sagittarius, tens of thousands of light-years from the sun. This proved the sun occupied an ordinary position far from the galactic center, another step in the long process of removing Earth and humanity from any special cosmic location. Shapley's distance estimates turned out to be too large by about a factor of 2, but his basic insight was correct. The clusters define a spherical halo centered on the galaxy's true center, and measuring their distances reveals the scale of the system they orbit. Modern measurements using Gaia and other instruments have refined the distances to globular clusters and revealed their orbits in detail. The clusters don't orbit in the disk's plane, but move through the halo on highly elliptical paths, swooping close to the galactic center and then swinging out to hundreds of thousands of light years before falling back inward. These orbits are shaped by the galaxy's gravitational field, primarily by the dark matter halo that dominates the total mass. By studying cluster orbits, astronomers can map the distribution of dark matter, inferring where mass must be concentrated based on how the clusters move. The results show that dark matter extends far beyond the stellar disk, forming a roughly spherical halo that might reach 1,000,000 light-years from the center or more. This raises an interesting question about the galaxy's size. If the dark matter halo extends to 1,000,000 light-years, is that the galaxy's true size, or is the galaxy defined by where stars are, in which case the size is closer to 200,000 light-years? The answer depends on what you're trying to measure. For understanding the galaxy's gravitational influence on nearby galaxies, the dark matter halo matters most. For understanding stellar populations and star formation history, the stellar disk matters most. There's no single correct definition, just different definitions useful for different purposes. The important point is that the galaxy's influence extends far beyond the bright disk, visible in photographs I, encompassing a vast region where its gravity dominates over the gravity of neighboring structures. You're lying in bed, and perhaps you're barely aware of the words now. Consciousness flickering like a candle in a draught, present for a moment and then gone. Your breathing is deep and slow, your body completely relaxed, settled into the mattress as if you're sinking slightly, held by gravity and softness. The story continues, but it's become like distant music, something happening in the background while you drift in that comfortable space where thoughts dissolve before fully forming. This is exactly where you should be, on the edge of sleep or already past it. And there's no need to pull yourself back toward wakefulness. Just rest here. The dark matter problem is one of the great unsolved mysteries in astronomy. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should, based on visible matter alone. Galaxy clusters hold together despite moving at speeds that should tear them apart. Light from distant galaxies is bent by invisible mass as it passes through galaxy clusters. All of this points to something massive and invisible, something that doesn't emit or absorb light at any wavelength we can detect. Dark matter appears to make up about 85% of the universe's total matter, with ordinary matter, the stuff that makes stars and planets and people, comprising just 15%. Yet we don't know what dark matter is made of, what particles compose it, or why it interacts so weakly with ordinary matter. For the Milky Way, dark matter dominates the mass beyond a radius of about 30,000 light-years from the center. Inside that radius, stars and gas contribute significantly to the total mass, but farther out, dark matter takes over. The galaxy's rotation curve, which plots orbital velocity versus distance from the center, stays roughly flat out to the edge of where we can measure it, implying that mass continues increasing even in regions where stars become sparse. This is the signature of a dark matter halo, extending far beyond the visible structure. Estimating the total mass of the Milky Way depends heavily on how far out you think the dark matter halo extends, and different studies give different answers ranging from 1 trillion to 2 trillion solar masses, with the uncertainty driven largely by uncertainty about the halo's size. The Milky Way exists within a larger structure called the local group, a collection of about 80 galaxies dominated by two large spirals, the Milky Way and Andromeda. These two galaxies orbit each other slowly, separated by about 2.5 million light-years, and they're falling toward each other under mutual gravitational attraction. In roughly 4 billion years, they'll collide, a slow-motion merger that will scramble both galaxies' disks and eventually form a single large elliptical galaxy. The outcome of that collision depends partly on the current sizes and masses of both galaxies. Recent work suggests Andromeda is roughly comparable to the Milky Way in mass, perhaps slightly more massive, which means the merger will be relatively symmetric rather than one galaxy clearly dominating the other. Understanding the Milky Way's true size matters for predicting what that merger will look like and what will survive it. A larger, more massive Milky Way would be more resilient to tidal disruption during the first close pass. The Sun will likely survive the merger, flung into a new orbit in the combined system, but its exact fate depends on details of how the collision unfolds. Most stars won't actually collide. Space is so vast that even in regions where two galaxies interpenetrate, individual stars pass by each other with enormous room to spare. But the gravitational interactions will scatter stars into new orbits, heat the disks, trigger bursts of star formation as gas clouds collide and compress, and eventually destroy the spiral structure of both galaxies as they settle into a new configuration. As your thoughts fade completely, as even the awareness of listening dissolves into the general awareness of rest, the galaxy continues its rotation far above, patient and vast. The measurement has been corrected, the error acknowledged, the map redrawn to show a structure larger than textbooks said for most of the 20th century. But the galaxy itself never changed. It was always this size, always this massive, always extending farther than early observations could reveal. Only the human understanding changed, slowly catching up to the reality that was there all along, waiting with infinite patience for better instruments and better methods to reveal what had been hidden by dust and distance and the fundamental difficulty of measuring something from the inside. You're back on Earth now, standing outside on a clear night far from city lights, looking up at the Milky Way's band stretching across the sky. The air is cool and still, and the stars are so numerous they seem to touch each other, forming a continuous river of light that arcs from horizon to horizon. This is the view humans have had for hundreds of thousands of years, the same pattern of light that ancient peoples saw and wove into their mythologies, the same glow that guided travelers and inspired philosophers. But now you know what you're seeing, the combined light of billions of stars in the disk, viewed edge-on from your position embedded within it, a perspective that makes it impossible to see the full spiral shape without traveling far beyond the structure itself. The fact that the galaxy is larger than long believed changes how it fits into the broader cosmic landscape. Galaxies are classified by their luminosity and mass, and the Milky Way is typically described as a large spiral, more massive than most spirals in the local universe, but not exceptionally so. If the stellar disk is larger than previously thought, that implies more stars, which means higher total luminosity and stellar mass. Recent estimates place the Milky Way's stellar mass at around 60 billion solar masses, with uncertainties of perhaps 20%. That makes it comparable to Andromeda, our nearest large neighbor, though probably slightly less massive. The revision upward in size and mass elevates the Milky Way slightly in the hierarchy of galaxies, making it a more substantial member of the local group than earlier estimates suggested. The size measurement connects to questions about the galaxy's formation history. Galaxies grow through two main processes: star formation from gas within the disk and accretion of smaller galaxies that fall in and merge. The relative importance of these processes varies from galaxy to galaxy. Some grew primarily through mergers, others through steady star formation. The Milky Way's history appears to involve both, with a massive merger perhaps 8 to 10 billion years ago that helped build the bulge and thick disk, and more recent smaller mergers that added stars to the halo. Understanding how much mass came from mergers versus in situ star formation helps astronomers understand the galaxy's place in the broader context of galaxy evolution. One way to probe this history is through stellar archaeology, studying the chemical compositions and ages of stars to reconstruct when and where they formed. Stars that formed early in the galaxy's history, before many generations of supernovae had enriched the interstellar medium with heavy elements, have lower metallicities than stars that formed more recently. By mapping metallicity as a function of position in the galaxy, astronomers can trace the inside-out growth of the disk, showing that the inner regions formed first and the outer regions assembled later. Gaia's data enables this kind of analysis on unprecedented scales, measuring not just positions and motions, but also colors and brightnesses that constrain stellar properties. You're lying in bed, and perhaps you're asleep now, or perhaps you're in that liminal state where dreams begin to intrude on waking thoughts, where the boundary between imagination and perception blurs. The pillow supports your head, the blanket holds warmth close, and somewhere in the background my voice continues. A steady rhythm of words that don't require processing, just a presence like rain or wind. If you're still hearing this, you don't need to focus. If you've drifted into sleep, the words will fade harmlessly into whatever dreams arise. Either way, you're safe here, comfortable, and the night holds you gently. The revision of the galaxy's size reminds us that even fundamental facts about our cosmic home can turn out to be wrong. Not because scientists were careless, but because the problem was genuinely difficult and the tools weren't good enough yet. This happens regularly in science. The age of the universe was once thought to be 2 billion years, then 10 billion, now about 13.8 billion. The value of the Hubble constant has bounced around for decades as measurements improved. Pluto was a planet, then wasn't, reflecting not a change in Pluto, but a change in how we define planetary categories. These revisions aren't failures. They're the natural process of knowledge refining itself, of errors being corrected as better data becomes available. What's striking about the Milky Way's size is how long the error persisted. The value of 100,000 light-years appeared in textbooks for most of the 20th century, taught to generations of students, repeated in countless popular science books and articles. The number took on a kind of authority through sheer repetition, becoming part of the baseline knowledge that everyone assumed was solid. It took decades of accumulated evidence from infrared surveys, radio maps, and finally Gaia's precise parallaxes to dislodge that number and replace it with something larger. The lesson is that even well-established facts should be held lightly, with the understanding that future measurements might revise them. The correction also highlights the importance of observing at multiple wavelengths. Optical astronomy alone couldn't reveal the galaxy's true extent because dust hides too much of the structure. Radio observations showed the gaseous disk extended farther than the optical disk, but gas isn't stars, so the measurement felt incomplete. Infrared observations detected cool stars in the outer disk that optical surveys missed, but infrared from the ground is difficult because of atmospheric absorption. Only by combining all these wavelengths, optical as infrared, radio, and adding precise parallax measurements from space, did the full picture emerge. Modern astronomy is inherently multi-wavelength, recognizing that no single band of the spectrum tells the complete story. The galaxy's size also connects to its role in the larger cosmic structure. The Milky Way sits in a relatively quiet region of space, part of the local group, but far from the massive galaxy clusters where collisions and interactions are more frequent and violent. This quiet environment has allowed the disk to form and persist relatively undisturbed, maintaining its spiral structure over billions of years. In denser environments, frequent collisions would disrupt the disk, perhaps transforming the galaxy into an elliptical or irregular system. The Milky Way's size and structure reflect not just its own history, but the history of its environment, the fact that it formed and evolved in a region where it could grow steadily without catastrophic disturbances until the future collision with Andromeda. As the story moves toward its end, as the last pieces of explanation settle into place, you might hold one final thought before releasing it into sleep. The galaxy is vast, ancient and patient, and humans are just beginning to measure it accurately after a century of getting it slightly wrong. The error didn't matter to the galaxy, which continued its rotation indifferent to human misunderstanding. But it matters to us, to the people trying to map their place in the cosmos, trying to understand the structure they're embedded in. And now the map is better, the measurement corrected, the number updated to reflect a galaxy larger and more complex than the neat diagrams suggested. That's a small victory for patience and precision, for building better tools and checking old assumptions, for the slow collaborative work of science refining its picture of reality, one measurement at a time. You're floating in intergalactic space now, millions of light years from the Milky Way, looking back at it as a distant spiral among countless others scattered through the darkness. From this perspective, the galaxy appears small and fragile, a pinwheel of light held together by invisible gravity, rotating slowly against the black. Around it orbit the satellite galaxies, small companions caught in the Milky Way's gravitational well, and beyond them the empty space stretches toward Andromeda, toward the other members of the local group, toward the vast cosmic web of galaxies strung along filaments of dark matter like dewdrops on a spider's web. This is the context the Milky Way exists within, not isolated, but part of a structure that extends across the observable universe, connected by gravity and history to everything around it. The question of why scientists got the size wrong for so long has a simple answer. Measuring vast structures from the inside is intrinsically difficult, and the error was hidden by systematic biases that affected every measurement method in similar ways. Dust made distant stars appear closer than they were. Selection effects meant surveys missed faint populations that traced the outer disk. Calibrations were based on assumptions that turned out to be slightly off. None of these were obvious problems at the time, and it took decades of improved observations from multiple independent techniques to reveal the biases and force a correction. The story isn't about failure or incompetence. It's about the patient accumulation of better data, the willingness to revise conclusions when new evidence arrives, and the fundamental humility required to admit that something everyone believed might be wrong. What changed wasn't just technology, but philosophy. Early astronomers worked with the assumption that what they could see represented most of what was there, that the galaxy didn't extend far beyond where observations became difficult. Modern astronomy assumes the opposite, that there's always more structure at the limits of detection, that the edge is never as sharp as it appears, that fainter populations exist beyond where current instruments can reach. This shift in perspective drives the push for ever more sensitive instruments, for space-based observatories that avoid atmospheric interference, for surveys that observe millions of objects rather than hundreds. The correction to the Milky Way's size reflects this broader shift from thinking we know most of what there is to know, to recognizing how much remains hidden just beyond our current capabilities. You're lying in bed, breathing so slowly now that each breath seems to take forever. And perhaps you're not really hearing these words anymore, just sensing them as vibrations, as rhythm, as something present but not requiring attention. Your body has settled completely, muscles released, weight distributed, warmth held close. The room around you might be dark or filled with soft light, but either way it feels distant, like something happening to someone else. If you're still conscious, it's just barely, a thin thread of awareness that could break at any moment and let you fall completely into sleep. And if you're already asleep, then these words are just dreams now, shapes without substance, fading as quickly as they form. The Milky Way continues its rotation, 170,000 light-years across or thereabouts, depending on how you measure and where you draw the boundary. The number will probably be refined further as more data accumulates, as Gaia continues operating and new missions launch, as methods improve and systematic errors are better understood. But the basic correction is solid. The galaxy is larger than 20th century textbooks said, not by a trivial amount, but by tens of thousands of light years, enough to matter for understanding its mass and structure and history. The error lasted nearly a century because the tools to correct it didn't exist until recently, and now that they do, the map has expanded to match the reality that was always there, vast and patient, waiting for human understanding to catch up. You're back in your room now, lying in the same bed where this journey began, but something has shifted in how you picture the space above you. The ceiling hasn't changed, the walls are still the same, but when you imagine the galaxy rotating overhead, it's larger now in your mind, extending farther than you'd thought, reaching out into darkness with spiral arms that fade gradually rather than ending cleanly. The mental map has expanded, not because the galaxy grew, but because the measurement finally caught up with reality. And in that expansion, there's something humbling and also comforting. The universe is larger than we thought, more complex than simple models suggested. And there's still so much we're learning about even the most basic structures, even the galaxy we live inside. The story of the Milky Way's size is really a story about knowledge itself, about how understanding develops through patient observation and willingness to revise beliefs when better data arrives. It's a story about dust hiding the truth and new instruments revealing it, about systematic errors that persist until someone builds a tool sensitive enough to detect them, about the gap between what we can see easily and what's actually there. The astronomers who measured 100,000 light-years weren't wrong because they were careless. They were working with the best tools available, making reasonable assumptions, following established methods. They were wrong because the problem was harder than it appeared, because nature hid crucial information behind veils of dust and distance, because the tools needed to see through those veils didn't exist yet. That's true of so much in science. The current understanding is always provisional, always subject to revision, always bounded by the capabilities of available instruments and methods. What we know today will probably be refined tomorrow, not because today's scientists are incompetent, but because tomorrow's instruments will be better. The Hubble constant will be measured more precisely. The distribution of dark matter will be mapped in greater detail. The merger history of the Milky Way will be reconstructed more accurately. And sometimes, those refinements will reveal that something we thought was settled actually needs significant revision. That's not a flaw in the process. That's the process working as it should, constantly checking itself, constantly improving, always open to correction. You're breathing so slowly now, each exhalation releasing a little more tension, a little more of the day's accumulated weight. Maybe you're asleep already, or maybe you're in that boundary state where you could go either way, where consciousness flickers like a candle nearly extinguished. The story is ending, winding down to its close, and whether you hear the conclusion or sleep through it doesn't matter. What matters is that you found something calm and vast enough to occupy your mind while your body found rest, that the galaxy's story gave you something to focus on besides the thoughts that were keeping you awake. And now those thoughts have quieted, replaced by images of spiral arms and dust clouds and patient measurements. And soon even those images will dissolve into the formless drift of dreams. The Milky Way is larger than the book said. That's the simple truth at the center of this long story. The error persisted for decades because measuring cosmic structures is genuinely difficult, because dust obscured the view, because the instruments weren't sensitive enough to detect faint stars in the outer disk. But humans kept building better telescopes, kept refining methods, kept checking and questioning, and eventually discovered the mistake and corrected it. The galaxy didn't change. Only the knowing changed. And that's how it always goes. The universe exists as it is, vast and patient and indifferent to whether anyone measures it correctly, while humans slowly build tools and gather data and refine their maps, approaching truth asymptotically, never quite reaching perfect knowledge but getting closer with each generation. Tonight, you've been part of that story, a listener in the dark while someone told you about spiral arms and parallax measurements and the slow, patient work of figuring out how large our cosmic home really is. So here we are at the end of the journey, and maybe you're still awake to hear this, or maybe you drifted off somewhere in the middle, lost consciousness during a description of dust clouds or infrared telescopes or Gaia's precise measurements. Either way is perfect. If you're asleep, these words are just dreams now. Abstract shapes flowing through wherever dreams come from. If you're still listening, you're probably in that soft borderland where thoughts dissolve before completing, where awareness flickers without quite disappearing. We've traveled from mountaintop observatories in the 1920s through decades of patient observation, through the launch of space telescopes and the discovery that the galaxy extends farther than anyone believed for most of the 20th century. We began with a question. What if the Milky Way is nearly twice as large as every textbook told you, and the mistake lasted for almost a century? Now you know the answer. The galaxy is roughly 170,000 light-years across, not the 100,000 that appeared in books for generations. The error came from underestimating interstellar dust, from selection effects that missed faint stars in the outer disk, from calibrations that were slightly off, from the fundamental difficulty of measuring something from the inside when dust and distance obscure the view. We trace the history of that error through Henrietta Leavitt's discovery of the period luminosity relation, through Harlow Shapley's mapping of globular clusters, through Robert Trumpler's proof that dust was dimming starlight, through infrared surveys and radio maps, and finally Gaia's billion-star census that revealed the disk's true extent. Along the way, we saw the human side of discovery. Astronomers spending cold nights at telescope eyepieces, developing glass photographic plates in chemical baths, measuring star positions under microscopes, building satellites and launching them to gravitationally stable points in space, writing software to process terabytes of data, arguing over discrepancies, publishing corrections, slowly converging on better answers. Science isn't a collection of facts handed down from on high. It's a process, messy and human, full of errors that get corrected and assumptions that get questioned and measurements that get refined. The story of the Milky Way's size shows that process in action, shows how knowledge grows not through sudden revelations, but through patient accumulation of better data and willingness to admit when something everyone believed turns out to be wrong. We floated above spiral arms and looked back from intergalactic space. We stood in observatory domes and sat in European control rooms watching data arrive from satellites. We traced stellar streams from disrupted galaxies and mapped the warp in the outer disk. We talked about dark matter halos extending to 1,000,000 light-years and about the future collision with Andromeda that will reshape both galaxies 4 billion years from now. All of it circles back to the central truth. The galaxy is larger than we thought, and the correction came because people kept building better instruments and kept looking more carefully, kept questioning the old measurements until new data forced a revision. You're lying in your bed, and the room around you is the same as it was hours ago when this story began. But something has shifted. Not in the physical space, but in how you picture what's beyond it, in the mental map that expands when you imagine the galaxy overhead. The ceiling is still close, the walls still confine the familiar space, but when you think of the spiral structure rotating above you, it reaches farther now, extends into darkness with arms that fade gradually, encompasses more stars and more space than the compact diagram suggested. That expansion happened not because the galaxy grew, but because the measurement finally caught up with what was always there. I want to thank you for spending this time here, for choosing this story as the thing to occupy your mind while you tried to rest. Maybe you were looking for something calm and vast to replace anxious thoughts, something scientific but not demanding, something that would fill the space without requiring effort. I hope it worked. I hope the images of telescopes and dust clouds and distant measurements gave your mind something to hold on to that wasn't tomorrow's worries or today's regrets, something neutral and patient, something that existed long before you and will continue long after. Indifferent to human concerns, but somehow comforting in that indifference. If you made it all the way here to the end, I'm genuinely surprised and grateful. Most people who listen to this kind of thing fall asleep partway through, which is exactly what it's designed for. The fact that you're still conscious, still hearing these words, is unusual, but also fine. Maybe tonight isn't a sleep night for you, or maybe sleep is approaching but hasn't quite arrived. Either way, you've journeyed through the story of a cosmic measurement, through observatories and satellites and the slow, patient correction of an era that lasted generations. And even if you don't remember the details tomorrow, even if all that remains is a vague impression of spiral arms and dust and distances, measured in thousands of light years, that's enough. Before you go, whether into sleep or back into the waking world, I'd like to ask something small. If you feel comfortable, leave a comment telling me where you're listening from and what time it is where you are right now. There's something strangely comforting about knowing there are people scattered around the planet, in different time zones and different circumstances, all listening to the same story about the Milky Way's size. Some of you are listening at midnight, some at 3 in the morning, some in the early evening before sleep feels possible. Some are in North America, some in Europe, some in Asia or Australia or South America. All of you sharing this moment of calm astronomy, this slow drift through the story of how scientists measured the galaxy wrong and then corrected it. And if this helped, if this kind of sleepy science brought you some peace or helped quiet your mind or just gave you something to focus on besides the usual nighttime thoughts, consider subscribing or leaving a like. It tells me there are others out there who want more nights like this, more stories that trade entertainment for calm, that prioritize rest over retention, that assume you might not make it to the end, and that's perfectly okay. These videos exist for the people who need something vast and patient in the small hours, who want to fall asleep learning about the universe even if they don't remember the lesson in the morning. The galaxy rotates above you right now, 170,000 light-years from edge to edge, give or take depending on how you measure. Billions of stars drift in their orbits, some near the center completing a circuit in a few million years, some far out in the disk, taking hundreds of millions of years to come back around. The sun is out there somewhere, about 27,000 light-years from the center, carrying Earth and you and everyone you've ever known through space at over 200 kilometers per second, all of it happening in patient silence, the vast machinery of gravity and motion continuing regardless of whether anyone understands it or measures it correctly. You're part of that structure, made of atoms forged in stars that died before the sun was born, arranged briefly into the pattern that thinks and feels and worries about tomorrow. Tonight you took a few hours to learn that the structure you're embedded in is larger than textbooks said, that the error lasted because dust hid the truth and instruments weren't sensitive enough to see through it, that better tools finally revealed what was always there. And now, whether you remember this or not, whether you fall asleep in the next minute or lie awake for another hour, you know that even basic facts about the cosmos can turn out to be wrong, that knowledge is always provisional, and that the slow work of science continues, patient and careful, refining maps and correcting errors and approaching truth, one measurement at a time. So rest now. Let your breathing slow. Let the weight of the blanket hold you. Let the pillow support your head. The galaxy will still be here in the morning, vast and ancient and patient, rotating in its billion-year cycle while you wake and go about your day. The measurement has been corrected, the map redrawn, and somewhere astronomers continue working, gathering data, refining methods, checking results. But that's their work, not yours. Your work tonight was just to listen, to drift, to let something vast and calm occupy your mind until sleep came. And now it's done. The story is finished. The galaxy is larger than the books said, and you're safe here in the dark, held by gravity and warmth, ready to let go and rest.